Ik zit eigenlijk een halve week. Nou. Leuk kader. Zoiets, ja, we hadden precies van het plan van
Please be seated. Welcome everybody. Happy to see a big group of people here. We are here for the public defense of PhD defense of Sjors Heefer on the topic of Finsler geometry, space-time and gravity, and a very long subtitle. So my name is Edwin van den Heuvel. I'm the Dean of the Department of Mathematics and Computer Science, and I will be chairing this session. Every defense, I think, is a very special occasion since it marks an ending of an intensive period of research, and we are very much looking forward to this defense. Have heard a little bit of the questions. I think we're going to have an interesting hour. So we are also very happy that we can do this completely physical. You know, COVID is taking, it's longer ago, but still, it's nice that we can do this again completely physical. I have a request. Please make sure that your telephone is shut down, not making any noise. It will disturb the defense. So I would like to officially now open the defense, and therefore first ask the candidate to come forward together with the seconds. Thanks. So we welcome, of course, the whole everybody here, but especially we welcome the committee members for joining this session, in particular those who are from outside the University of Eindhoven. We, as a university, very much values the presence of experts from outside for these defense committees, and I would like to mention that this is always a very time investment, is very considerable. Not just by reading the thesis, but also preparing and come here, and therefore it's very much appreciated that we have such an interesting committee also from outside. I'd like to introduce, first of all, the first promoter, Professor Florak, the co-promoter, Dr. Fusten. We have the secretary, Professor Toshi, and on the other side we have Professor Cavalcanti from the University of Utrecht, Professor Sanchez from the University of Granada, Dr. Voicu from the University of Brasov, and Dr. Fiver from the University of Bremen. So welcome. I would like to start the defense at this point, so I will ask the first promoter to give the first question.
Okay, thank you. Geachte promovendus, you have written a very, very nice thesis, and we discussed it thoroughly. I would like to ask you to give a presentation in 10 minutes to explain what you did for the audience and the committee.
Okay, the promoter, thank you for your question and for the nice compliments, and I will. Well, first of all, it's great to see so many familiar faces here, and my goal for the next 10 minutes is to give you all an idea what my thesis is about and what I've been up to in the last couple of years. So I want to dive right in, starting with Einstein's general theory of relativity, which really lies at the basis of all of this. So this is the revolutionary theory of gravity that Einstein came up with a little over 100 years ago. And the important message of this theory is that we should not think of gravity as a force. Okay? Instead, we should think of gravity as a manifestation of the geometry of space and time. Or really even, I should say, of space-time, which is what you get when you put the 3 dimensions of space and 1 dimension of time together into one 4-dimensional continuum. So here on the slide, you see the Earth and the Moon, and even though space-time is really 4-dimensional, we cannot visualize that. So here we represent space-time as this 2-dimensional grid. And according to general relativity, whenever you have a massive object in the universe, like the Earth, then space-time will actually curve around that object, creating a non-trivial space-time geometry. That's what you see here, and that's actually what we understand as the gravitational field. At the same time, any object that moves under the influence of gravity, so the Moon in this example, will actually simply take the straightest possible path through space-time. And the catch is, of course, that space-time is curved, and that means that straightest possible paths do not actually look straight in the typical sense of the word. So for the Moon in this case, the straightest possible path through curved space-time turns out to be a circular orbit around the Earth. And we all know that's how the Moon moves, and this is the real reason why it does. So in this way, general relativity beautifully explains this and also many other gravitational phenomena. Okay, now I want to dive a little bit deeper. So mathematically, everything we just discussed is captured very precisely by Einstein's field equations. I'm not going to explain everything in detail here, but the most important object is this G, the so-called metric tensor. If we know this G, then we know everything there is to know about the geometry of spacetime. So that means that if we want to figure out what the geometry of spacetime actually looks like in the vicinity of the Earth, in this example, or in any other part of the universe for that matter, then what we have to do is we have to solve this equation for G. Okay? That's the name of the game. Now, this is actually incredibly difficult to do in general, and the reason is that the other quantities appearing in this equation actually depend in a very complicated way on G as well. No one ever shows you this in popular talks or popular videos, but if you write everything out in terms of the metric tensor, then Einstein's field equations actually turn into something like this, which looks a lot more daunting, right? And what makes it even worse is that it's not just a single equation either, it's actually a system of 10 equations, namely one for each value of the Greek subscripts mu and u in a certain range. So as you can imagine, this is not going to be very easy to solve. And much of my research has actually focused on solving not exactly this equation, but a generalized version of it, which we'll get to in a second. Because the thing is, even though general relativity has been incredibly successful, the theory also really has some substantial problems. And one of the most important ones of these is the clash with quantum mechanics, another extremely important fundamental theory of physics. So the point is basically the following. Everything that happens in the universe is somehow a manifestation of one of the 4 fundamental forces of nature, or several. And these are shown here on the slide. So gravity and electromagnetism are very familiar. And then there's also the creatively named weak force and strong force, which are at play mainly in the nucleus of an atom, for instance. With the exception of gravity, all of the fundamental forces, as well as all known types of matter in the universe, all seem to be governed by the laws of quantum mechanics, which are strange probabilistic laws that fortunately we do not have the time to get into more detail. And gravity really seems to be the only thing in physics, the only thing in nature that does not seem to fit into this quantum mechanical puzzle. Even though we're pretty sure for mathematical consistency reasons and various other reasons that it should fit somehow. So this is a big fundamental problem. It's called the quantum gravity problem. And well, one of the approaches to solving this problem is by modifying the classical theory of gravity, which is general relativity. So what do I mean by this exactly? Well, traditionally, general relativity is formulated in terms of a certain geometric framework called pseudo-Riemannian geometry. And we can simply think of this as a mathematical language in which we can describe most of the typical types of geometries that you encounter. For instance, the one in the image on the left here. Quantum gravity research suggests, however, that the spacetime in which we actually live might have a geometry which is beyond the scope of this traditional language. And that would imply that to describe our actual universe, we would need to resort to a more powerful, more advanced mathematical language, namely one known as Finsler geometry. This would of course be a problem for general relativity. But the good news is that general relativity can actually be reformulated beautifully in terms of this language of Finsler geometry. And that gives us a new theory, an extended theory of gravity, called Finsler gravity, and that's really the main topic of my thesis. So essentially, Finsler gravity is basically the same theory as general relativity, but it's written in this more powerful mathematical language, making it a richer theory. So I asked ChatGPT to help me visualize the difference between the two geometric frameworks. For technical reasons, it's not actually possible mathematically to visualize Finsler geometry. So that's why the image on the right may look a little bit funny, and we have to take it with a grain of salt. But I do think, as an artist's impression, it's actually very nice, because what it does convey is that there's just a lot more... Whoops. Excuse me. There's just a lot more going on the right-hand side, right? We see some trees, we see a river which is flowing, so there's also really some directional information going on there. Technically, that's actually very relevant. It's one of the defining properties of Finsler geometry. And indeed, in Finsler geometry, there's just a lot more room for this kind of intricate detail, which is exactly what leads to a richer theory. Okay, good. That brings me to my last slide already. So this is one of the main questions that I tried to answer in my thesis. So according to this extended theory of gravity, what does the geometry of spacetime actually look like? And that's specifically in the case when there's no matter around, so in a vacuum or an empty space. Now, as we discussed, in order to answer a question like this, we have to solve the field equations. And in this case, it's going to be the Finslerian analog of Einstein's field equations. So in practice, I spent a lot of time investigating the mathematical structure of this equation, finding solutions to it, classifying solutions to it, and then also really trying to understand what these solutions mean physically, right? That's extremely important. So as an example, one class of solutions that we found actually described gravitational waves, which are ripples in the geometry of space-time that travel through the universe at the speed of light. And you might have heard that in 2015, which is about 9 years ago, such waves were actually directly detected for the very first time. And this was an incredible achievement. And what our results show is that these first detections, as well as the detections that followed, are actually consistent with the idea that indeed our space-time might have a Finslerian nature. Another solution that we found describes a whole universe, which starts in a Big Bang, then expands and keeps expanding. And, well, these two examples really speak to the imagination. A large part of the thesis also focused on abstract mathematical properties of these solutions, and also of Finsler geometry and Finsler gravity in general. So that's a little more difficult to convey here in 10 minutes. So I'm not going to try to do so, but I hope that I've been able to give you some idea at least of what the thesis is about. And I'll stop here.
Thank you very much. Is the first promoter happy with the answer?
I'm happy with the answer. Just maybe one comment. I think there's an interesting paradox between your last slide and the quote by Wheeler, but we can talk about that a little bit later. I have to
Very
do it
curious.
back in German. Thank you for your presentation.
Thank you very much. So we would like to continue the defense and would like to ask, I have to put on my glasses again, ask Professor Dr. Sanchez to start the defense on the topic.
Thank you first for this nice presentation. I would like to congratulate for your remarkable work. Your thesis represents a significant advance in the development of Finslerian extensions of general relativity. Can you?
Yeah.
Okay. You were saying that your thesis represents a significant advance in the development of Finslerian extensions of general relativity. The work is complete and thorough, ranging from purely mathematical aspects to observational issues. And this is certainly very noticeable. In particular, you find new, well-motivated solutions of the Finsler-Einstein equations, both extending the classical relativistic ones and also those with a relativistic counterpart. But I think that it is also no less important that the writing of the thesis is enlightening, mathematically rigorous, and pedagogical, going far beyond the simple addition of previous publications. I, in fact, would recommend you to put this available publicly, because this will be very useful for the community. Well, I would like to ask you some questions mainly related to the metrizability problem. You proved that the connection of a Berwald metric may have a non-symmetric Ricci tensor, rendering it non-metrizable. And well, you give examples in generalized and combinametrics, also introducing the thesis. These are very good and surprising results, and as a consequence, you pose the question: are metrizable all the indefinite Berwald metrics with symmetric affine Ricci tensor? Okay. Well, I think that this question is posed perhaps should be decomposed in two parts. The first one is the question if are metrizable all the indefinite Berwald metrics with domain the whole tangent bundle. Because in the other case, as you prove necessarily, your counterexamples are not defined in the whole tangent bundle. I think that in some sense this case, which is a particular case of your general question, will be especially important. I think that as you do have unicorns in the last case, the existence of these examples, which would be Berwald metrics, non-metrizable on the whole tangent bundle, would be some sort of unicorns there. So, first I would like to ask you if you have thought specifically this question, and on the other hand, about your question, you have referred to the non-symmetry of the Ricci tensor. I'd also like to ask you if this is just a sufficient condition for non-metrizability, but you can think in our different abstractions. Okay. For example, if you consider the parallel transport on the tangent bundle, the metric is not defined on the tangent bundle, then the parallel transport should carry the tangent bundle, the domain of a point to the domain in another point. So perhaps this question would be necessary to pose more preparedly your original question.
Oh, great opponent. Thank you very much for your question and for your nice compliments. It's interesting that you ask this question because I know that Dr. Voitu has actually recently had a publication on this very issue. So I posed the hypothesis that indeed I expected that perhaps in order to have metrizability you would need to have this symmetric Ricci tensor. Well, sorry, that's the easy direction. I thought perhaps if we have a symmetric Ricci tensor that would imply metrizability. What Dr. Voiku showed very recently is that this is not the case. At least not in the case where you are not defined on all of the tangent bundle, which is also what you suggest. So the question for Finsler metrics defined on the entire tangent bundle is still open, I would say. But it turns out that you can have Finsler metrics that have a symmetric Ricci tensor and that are still not metrizable. So we have some counterexamples of that.
Yes, I think so. The point is that now one has to reformulate this question the system of local abstractions to
Yes.
metrizability, and eventually this global property definition.
Right. That's another very good question, and I haven't thought about that at all, to be honest. So until so all results are for local metrizability in my thesis, and the question whether it extends globally, I honestly have no idea whether that would be possible. At least not in general. Perhaps on a case-by-case basis you can say something, but in general I think so far that's very difficult.
The existence of local but not globally extendable examples, locally but not globally metrizable examples.
I think, so there's one example in the thesis, I think, which is locally metrizable and not globally. Let's see. So that would be chapter 6. And then I think we can go to the simplest case, metrizability of M-propina spaces. Let me see what here I'm referring to. Okay, yeah, so theorem 6.2.3, sorry, that took a while. In the third point, in equation 6.18, we give an explicit metrization of a generalized M-propina metric. So it's on page 82, equation 6.18. We give an explicit metrization, A tilde, of the metric that's built from A, let's say. The Finsler metric that's built from the procedure Riemannian metric A. And this is a local metrization, but in general, because the function rho and the integral is defined in a chart, a local chart, you cannot extend this globally. Now, that's not proof, of course, because you might have luck that it works out, but I think you can choose the function rho in such a way in the chart that it cannot be extended to the whole manifold. That's not the complete answer yet, because this is also just one example of a metrization, and it might be the case that there exists another metrization which is extendable. So I don't have an example which definitely does not extend, but I think you can build something here which does not extend globally.
Thank you very much. I would like to continue the defense with Professor Dr. Voiku from the University of Brussels.
Dear candidate, I would start first by underlining what the previous speaker said about the qualities of your work. The thesis is indeed the result of a huge work, which I totally appreciate. It shows a deep understanding on the intricate nature of indefinite Finsler geometry. And this understanding, I would say to the whole public, is deeper than the one of most experienced researchers. So I really appreciate that. And now my questions are going to be, at least the first one will be quite technical and very related to Professor Sanchez's one. So it's still about metrizability versus symmetry of the connection Ricci tensor. So indeed, you are very much aware of the newest results. We did prove that the symmetry of the Ricci tensor is not a sufficient condition for the metrizability, the local Riemann metrizability of a given symmetric affine connection. At play, actually, there is another actor, which is the holonomy algebra of the connection, namely the dimension of the vertical part of the holonomy algebra generated by the Lie brackets of the horizontal basis vector fields. And we actually showed that Ricci symmetry and the dimension of the vertical part of the holonomy algebra are independent conditions. So there are two actors at play, one of which is the symmetry of the Ricci tensor, the other is the dimension of the holonomy algebra, which should be non-maximal, so as to allow to choose the direction dependence of L quite freely. And my question now goes, okay, since we know that these are different things, did you try to relate the symmetry of the Ricci tensor to the invariance of the Finsler function, the original Finsler Berwald function, with respect to some vertical pseudo-orthogonal group? I would really suspect that Ricci symmetry could be the result of such an invariance. Did you ever try to see if this is true or not?
Sergey, the opponent, thank you for your question and thanks for the very nice compliments. No, I didn't look into this. So what you're saying is that you have the symmetry of the Ricci tensor on the one hand is unrelated to the dimensionality of the vertical part of the holonomy algebra. And you're wondering if the symmetry of the Ricci tensor is related to the
invariance of the connection, actually, under some pseudo-orthogonal group.
Of this holonomy group specifically?
Yes,
or?
yes. So you have kind of, say, pseudo-Riemannian holonomy.
No, I didn't look into this at all. But I think this would also play a role in the global aspects, right?
It should.
But apparently, as you're saying, it also plays a role in the local aspects even.
Yeah, apparently yes. I don't know the answer. I saw that maybe you have looked, or you could look, maybe.
Yeah, it sounds very interesting. Yeah, no, I haven't looked into that yet at all.
All right, then a second question is about the physical interpretation of the metrizability, I mean, local or global Riemann metrizability of a connection that is already Finsler metrizable. And again, so the counterpart is the physical interpretation of the lack of Riemann metrizability of an affine connection.
Yeah, so why would it be a good physical condition, for instance? This is an extremely good question, and unfortunately I don't have a good answer. I've thought about this a lot, but I haven't been able to come up with a good reason why we would actually want metrizability. So it's mainly, mathematically, it's just very convenient. It's a nice property to have. And perhaps, one thing that I might think about is that sometimes you want an inner product on your value spaces. The problem in Finsler geometry is, of course, you have a range of inner products. So one nice aspect, if you can metrize your space by a pseudo-Riemannian metric, you will get one fixed pseudo inner product on each tangent space, which might be useful for something. Don't know what, but that's one thing I can think of that you might want physically. But apart from that, honestly, I think it's just a very interesting mathematical question. I'm not sure whether physically it's
actually in most physical contexts, you have spherical symmetry or cosmological symmetry. You do have some fiducial Riemannian metric. And you may have on top
True.
some Finsler metric, so you can compare the affine structures, maybe something comes out of this comparison.
Right, so you mean you start with a pseudo-Riemannian metric, then you make it into a Finsler
So
metric,
your
and
alpha
then...
beta metrics are obtained by
Right.
deforming a certain pseudo-Riemannian
Yes.
metric in the end.
Yes, and then it's very interesting whether the metrizing metric is the same as the original one, which in some cases that we discussed it is, and in other cases it isn't. So it would be extremely interesting to see whether that makes some physical sense.
Could you point out, for instance, some effects of having the pseudo-Finsler metric and the pseudo-Riemannian metric with the same canonical connection, so with the same parametrized geodesics that are finally equivalent?
Could you say that again?
So if you have, say, a Finsler metric and a Riemann metric that have the same affine structure,
Right, yes.
but still different cones, that would point out some
Yes.
Eulerian effects.
Exactly, and that's one of the examples that we actually have, the gravitational waves solutions. They have exactly the same affine structure, so they have exactly the same geodesics, but because the null condition is slightly different, light rays actually take a different path. So, yes, there are actually some differences there.
Okay, and last question, if I have some 1
Go
minute left. So you have a very nice round thesis of 10 chapters. What would an 11th chapter look like?
Ooh, an 11th chapter. That's a good question. An 11th chapter. So what's next?
Yes. What's next?
Well, what I want to look into more is cosmological and spherically symmetric solutions. I know that you're also working on this, and this would be extremely interesting to look into. So we already have quite some results. You have a lot of results, and other people here as well. So it would be interesting to start from these symmetries, let's say cosmological symmetry, and then try to find solutions to the field equations that have those symmetries. So far, for instance, in the case of cosmological symmetry, we already have the most general Berwald solution. So it would be interesting to go beyond that, perhaps to Landsberg spaces or even more general. We may start with this in, I think, the last chapter here. But I think there's a lot more to do in that direction.
Do you have in mind only vacuum solutions or, say, kinetic gas solutions?
So, I like the vacuum solutions because they're so nice and simple. At some point we need to go also to the matter solutions, of course. Then I first need to study that in detail. I don't feel like I understand that well enough yet. But at some point, yes, of course, we should look also at matter solutions. Especially in the cosmological case, that would be interesting. But vacuum solutions, they span a large range of physical situations, right? Even outside spherical mass, everything is vacuum. So vacuum already is very nice, I think.
Thank you.
Thank you very much. We'd like to continue with the events with Dr. Pfeiffer from the University of Bremen.
Geachte promovendus, I also can agree only with my with the previous speakers that I really enjoyed reading your thesis. It's an amazing piece of work. It's really a pleasure to read it, and also thank you very much for the nice introduction today in the talk. It was amazing. So just continuing with what you said about deformed light cones, and can you make a connection there between Finsler geometry and approaches to quantum gravity?
With the deformed, sorry.
For example, so the question is there a connection, or can you pinpoint a connection there between Finsler gravity and approaches to quantum gravity?
Zeer geehrte opponent, thank you for your question and for the nice compliments. So, a connection between Finsler geometry and quantum gravity. Yes, so there are several results in quantum gravity that you start with not a fully fledged theory of quantum gravity, but let's say the best we can do. For instance, in 2 dimensions, we can make good mathematically consistent theories. And if you take certain classical limits of these theories, then what you get is actually, you would expect to get Minkowski spacetime, some kind of classical theory. Turns out that in a lot of limits, you actually get a deformation of Minkowski spacetime. Very well known one is the Kappa-Minkowski or Kappa-Poincare model. And these models can be described using Finsler geometry. So pseudo-Riemannian geometry is not enough to describe those models, so general relativity will not do. But Finsler geometry and Finsler gravity seem to be adequate to handle those cases. So that's actually one of the big pieces of motivation why I think Finsler gravity is important to look at.
Yes, thank you. And then we talked about the metrizability of Berwald spacetimes, which are a very special class of Finsler geometries. So there are other classes, so one can classify Finsler geometries according to how close they are to Riemannian geometry in some sense. Can you say what the other classes are?
Okay, so we could start indeed. Okay, so we have pseudo-Riemannian, that's general relativity. And we have one step up, we have Berwald spaces in some sense. Then we can go to Landsberg or even weakly Landsberg, which is in between. Sorry, it's not in between. So you have Berwald, you have Landsberg. If you want to go more general, you have weakly Landsberg. And I think those are the first classes to look at next. Then, of course, in the end, it would be great if we could do something completely general. So, for instance, gravitational waves, for instance, we don't want to put any restrictions on the metric, basically. We just want to say, let's start with some, let's say, Minkowski spacetime, and then some very small Finslerian perturbation, which is completely general. And perhaps in that case, we might actually be able to find some nice results in general, because it's only the first order. That would be nice. But yeah, in cases of spherical symmetry, cosmological symmetry, it seems that's extremely difficult, and that's why Landsberg or weakly Landsberg might be a good thing to look at next.
Yeah, in particular, when you look at the field equations, why are they very interesting or promising?
In those specific cases, you mean?
Yeah, for the weakly Landsberg.
So, okay, so the field equations, if you have a weakly Landsberg space, then the whole term on the right-hand side, or on the left-hand side, on the right, vanishes, and so it becomes a lot simpler. We only keep the Ricci tensor term, which makes everything a lot simpler.
Yeah, do there exist solutions, or you found solutions beyond Berwald spacetimes, so Landsberg solutions?
Yes.
Where can you apply them in physics?
So in the last chapter, chapter 10, we have a unicorn solution, which means it's Landsberg, but it's not Berwald. So it's strictly more general than Berwald spaces. And so the interpretation of this solution is that it's useful in cosmology. It describes an expanding universe, which expands at a constant rate, which is kind of interesting. And that's also because we found this example, it might be very interesting to look further into these Landsberg spaces, because it seems they have certain mathematical properties which allow for this kind of solutions to the field equations, also with nice light cones. And
yes, what would make these solutions physically more applicable, so or more realistic to really describe the universe? So these solutions are very nice, but I think you partly said it already. Let's pinpoint this one more time. So what is missing to give a real description of the universe?
I'm not completely sure what you're hinting at, but perhaps one of the issues, I don't know the details of this, but I think that there are problems if you look at Berwald spaces, only Berwald spaces, and you put a matter term on the right-hand side of the field equations, perhaps that's what you mean, then we don't seem to get any interesting results. So in that case, we might need to go more general and go to Landsberg spaces.
Yeah, but so the Landsberg space you found, this is a solution of the vector equation.
Yeah, they can also be solutions to the vector.
Yeah. But so what's missing is the meta. So we need to find.
Right. Yes. At some point, of course, we want to add matter. Yes. The Landsberg spaces seem better equipped to do that.
Yeah. Okay. Thank you very much.
Thank you very much. So let's continue with the fourth questioning. Professor Dr. Cavalcanti from the University of Utrecht.
Dr. Provendus, it was a pleasure to read your thesis. I'm not an expert in Finsler geometry, so I also thought it was nice. It was very accessible for just people with general geometry knowledge. It was very interesting and full of results. Thank you very much for the opportunity. That has already been discussed, and okay, so it's coming from a non-expert. You have to bear that in mind. So right now we have found vacuum solutions for Einstein equations. Do you see the possibility of is the possibility of Finsler geometry actually helping with current things that physics struggle just with general relativity, such as dark matter, dark energy. Is there something, because right now in Riemannian geometry that's a problem, what in Finsler geometry could possibly contribute to be a solution if there is no dark matter, for example?
Right, that's a good question. I don't know the details of this. I know there is some literature on it. So apparently you can somehow use Finsler geometry to explain away dark matter and dark energy. I don't know the details, so unfortunately I can't tell you that. Perhaps, if you're thinking of dark matter, perhaps there's some preferred rest frame of the dark matter in the universe. And we cannot, so you would need a kind of directional dependence to describe that. And perhaps that's one thing I can think of Finsler geometry might be able to help with, because we have exactly these directional dependencies in the geometry. Apart from that, I don't know.
Okay, but at the same time you have a chapter that says that on Earth, if you look around, we cannot really measure the difference between Riemannian, between normal general relativity and Finsler.
Right, yes.
So,
in the gravitational wave case, yes.
Okay.
Yeah. So that's specific to these gravitational wave solutions that we found, because we were very interested what's the physical difference between these Finslerian things and Riemannian things. And it turned out we did the calculation and there was no difference. So as far as we know so far, perhaps there might be other effects, but yeah.
Moving on, you do this alpha beta metrics, so they are all over the thesis. And of course we will be interested in general, like that was a previous question, like more general types of Finsler metrics. And if I was to stick with alpha beta, what would be the next step? I know gamma delta, but are we going to, like, if I was to try to generalize it from that point of view, would be polynomial, would be degree 3? How far are we from just putting a smooth function there? So like the next step into studying this.
So you want to stay in alpha beta, or the next
no,
step?
leave alpha beta. So you have
Leave
a linear, have a quadratic term, and are you going to do now a cubic term, or are you, like the plan would be to at least have a polynomial, or at some point just a function?
So one other interesting case is that instead of beta being in one form, you take beta being another Riemannian metric, or pseudo-Riemannian metric. And I've tried to look at this, but it was computationally quite difficult. But it might still have some physical relevance, because you start from some pseudo-Riemannian thing, which you understand, and then you add something which is slightly different. So that would be a variation on the alpha-beta metric. You can also generalize the idea of an alpha-beta metric by letting alpha be a Finsler metric. And then, so you start with some Finsler metric, and then you add this one form, and then you can do that repeatedly, and you get new classes of Finsler metrics each time, for which kind of nice results are known, comparable to alpha-beta metrics. So that would be one idea. What we want to achieve is that I think we want deformations of general relativistic spacetime. So we want to start, we don't have to, but it's nice to start from some general relativistic spacetime and apply some small deformation. And those kinds of geometries are well suited for that.
Which brings me to my next question. In all sorts of geometric structures, we have deformation theory, in which you really try to describe nearby solutions to your equations, modulo whatever is the equivalence relation for them. What is there a general deformation theory for Einstein solutions here of Finsler metrics?
Not that I know of, no.
Okay, so it's not like we do not know if it's going to be finite dimensional or.
No, I expect. So basically, if I rephrase what you're asking to see if. So I think you're asking that starting from some Einsteinian solution, let's say, to general relativity. In how many ways can you inequivalently deform it? And would that be infinite or not? I expect it's infinite, because if we look, for instance, at the PP waves that we discussed in the thesis, then one thing we showed is that basically for any alpha-beta metric, we can deform it. And the alpha-beta metric depends on some function phi, right? And we can choose basically any phi up to some constraint. So it seems that that would definitely be an infinite dimensional way of possible ways of deforming of deforming the metric. I don't know whether some of those might be asymmetric. I don't know.
Yeah, so that's the question, like what's
Yes.
the notion of equivalence? Because often all these things, if you apply a different morphism, you always get infinitely many different looking things, but then there's what's the notion of equivalence, and also if you start doing Finsler geometry, you want to do the notion of equivalence a bit more general than just different morphisms.
Right. Well, so in general relativity, it's very similar. So in general relativity, we would say two metrics are the same. We have a diffeomorphism between the manifolds,
Geometry, yeah.
and then metric is pulled back.
Mm-hmm.
Finsler geometry would also ask there to be a diffeomorphism. Then we need to lift that to the tangent bundle because the Finsler metric is defined on the tangent bundle. Then the Finsler metric needs to be pulled back. That's a natural generalization of that.
By the derivative of the map, or you can allow yourself to just a bundle automorphism of the tangent bundle different from the underlying diffeomorphism.
I think you do want a diffeomorphism on the base manifold.
Okay.
Because you really want spacetime to be mapped to spacetime in some way. I think that's important. Yes. Yes.
Okay. And then we can still infinitely many. I don't know if I have time for.
Yeah.
So
One question.
Yes, it's a short one and a bit of a precise one. I was looking at page 68, theorem 5.3.12. And you say there are two equivalent things, 1 and 2, and the number 1 is f is Berwald, okay, so that I understand. And then there's some further condition which goes to equation 5.46. Can you kind of give me some insight of what that restriction on the Berwald metric means?
Right. So the reason why we introduced this in the beginning is that we have a Finsler metric that depends on alpha and beta, so it's natural to expect that this deformation tensor, this T, will also depend on alpha and beta in some way. And then our idea was to write down the most general tensorial expression in the quantities alpha and beta. Now, this is not completely most general, because you can also put derivatives of beta in there, for instance. But as long as you don't take derivatives, this is the most general tensorial thing you can write down in terms of alpha and beta. So that's the reason why.
Okay, well that helped me to understand. Thank you. I think that was all.
Thank you very much. So let's continue with the defense with Professor Dr. Toshi from our university.
Thank you, Ella, Meneer Director, Jarte promovendus. So I would like also to congratulate with your work. It was a pleasure to read it. I learned a lot from it. But still I have some questions. And, I would like maybe to continue along the line of my colleagues about the possibility to actually measure yourself if our universe is following a Finsler geometry or general relativity. And so when I read the conclusion of your chapter 9 about the computational gravitational wave, the result is negative, but you are it sounds very optimistic. And aside from the computational gravitational wave, that you say that it doesn't exclude, right, the possibility to have Finsler gravity, you mention other things like black holes. You mentioned that you are actually working on that, and then you say that there could be also other possibility to probe the Fislerian character of spacetime in other ways. We have not discussed possibilities, but we will certainly do so in the future. And so I would like to hear from you what you think, which direction you think are more promising indeed to see or to put a bound, for example, on this.
Okay, the opponent, thank you for your question and for the nice compliments. Well, one thing that I think would be very relevant to do is to look at, as you say, at spherically symmetric solutions, so for instance black hole solutions. And then if we understand that better, and we can even understand if you have two merging black holes, how that would produce some waveform, gravitational waveform, then we could, using the results that we sketched in that chapter, we could actually figure out if the waveform comes from a general relativistic process, or there are some Finslerian effects in the generation of the gravitational waveform. So I think that would be extremely interesting to look at. It's also extremely difficult to look at. So start has been made by some of our colleagues here, but we have a lot to do in that direction. But I think it's extremely interesting to look in that direction.
Thank you. So black holes are probably the direction you like to look at, right? The second thing, so I guess that you respect this question from me. We are very interested in conducting experiments on general relativity. So, do you see possibility to have water analogs from Finsler gravity? What would you do? What would you think about?
That's a good question. I have thought about it a little bit. So the thing in the Riemannian case, it's nice because if you write down the equation of fluid dynamics, you can rewrite it into some Klein-Gordon equation on some curved spacetime. The thing is, there's no directional dependence in that Klein-Gordon equation. So there is at least not directly a way that we could put a Finsler geometry there, because then the Klein-Gordon equation, well, first of all, we would have to define what we mean by the Klein-Gordon equation in the Finslerian case. I do not think this is obvious. There might be several inequivalent ways of defining it. But even if we had it, then there would probably be factors of y, so directional dependencies in that Klein-Gordon equation, meaning that it would never coincide with the actual fluid dynamics equation. So I don't see a way to directly generalize this, but I don't know that much about fluid dynamics. Perhaps in fluid dynamics there are specific cases where there is actually some specific directional dependence in the fluid, and in such cases, it might be very relevant to look into Finsler description of those processes.
Indeed, there are many different fluids, so I'm sure that one could figure out that to produce directional dependency of anisotropies. And so which type of phenomenon would you like to? Propagation of waves or?
In an analogy, still.
Analogies, yes.
Well, because we now understand, due to our project, we understand the general relativistic case a bit for these waves on the water. I think it would be nice to generalize exactly that analog. If there were some fluid that would indeed have directional dependence, that would be the first thing I would look at.
Thank you. Do we have time for one? Okay. Another thing that I was actually very interested in is from the purely point of view of the mathematical formalism. I wonder if this can be useful or if it is currently being used in other applications in physics or in science in general. So, are you aware of application of Finsler geometry outside of?
Yes, so some colleagues of mine, my Berwald actually, they're working on, for instance, geodesic tracking. So they're looking at the brain, for instance, or blood vessels, and they're looking at the veins or the nerve bundles. And usually this works using Riemannian geometry, that's the classical paradigm. And basically, let's say a vessel would be a geodesic in some Riemannian geometry, but my colleagues are looking at Finslerian generalizations of this, and so that's one application where this is used.
Okay, thank you. So I should ask them.
Thank you very much.
Thank you very much.
Thank you very much. Would like to continue the defense with Dr. Fuster.
Geachte promovendus. So of course I would also like to congratulate you with this impressive piece of work that I have followed very closely during the past years. But also as my colleagues, I have still some questions for you. And we already talked a little bit about the different types of solutions to the field equations in vacuum. And we have been able to find solutions of Berwald type, solutions of non-Berwald Landsberg type. And we also talked a little bit already about the case of weakly Landsberg spaces. So I think that that's probably the next step in trying to go to more general solutions. So I was curious if you're aware of any results on weakly Landsberg spaces that we could try to use as an ansatz for the field equations in vacuum.
Sergej the co-promoter, thank you for your question and for the compliments. Well, the most important result we already discussed, like the field equations simplify a lot, so that's nice. Whether there are actually any other results in general, I'm not sure, to be honest.
So I think, for example, when we were looking at the unicorn case, what we did was, okay, first we noticed that there was a space-time which was a unicorn, and then we thought, okay, let's see if we can use this as an answer for the field equations in vacuum. So are you aware of any similar results?
Specific cases that we might try.
Yeah, exactly, in the case of weakly Landsberg spaces.
Well, there are some more unicorns that might be interesting. I think they're computationally more difficult. So
But I'm not talking about unicorns, I'm really talking about the non-Landsberg, weakly Landsberg case.
weakly Landsberg case, yes. But I think some of those unicorns, I'm not sure if they're all Landsberg. Some of them might be weakly Landsberg. I'm not completely sure from the top of my head, but I'm pretty sure there probably exist weakly Landsberg unicorns in the literature that are not Landsberg. I think they're even in the paper when they basically write them all down. So we might have a look there.
Okay. So by preparing for this session, I also found some alpha beta metrics. So I thought that maybe that could be something interesting that we could take a look at. So some alpha beta metrics which are weakly Landsberg, and the difference is that the one form beta is non-parallel. So that would be also an extension. It's also related to one of the questions of how to generalize alpha beta spaces. Okay, then I will also, I think I still have time for this one more question. So I would like you to take a look at equation 7.7. And this is the field equation in the positive definite case. So we haven't really, been taking a look at this equation, but I think that it would also be interesting to find solutions to this equation. And my question is actually related to whether you think that it's possible to find solutions of Finsler-Einstein type to this equation.
Right, yes, I agree. This will be extremely interesting to look at. The problem is the methods that we used will not directly work because the basic results that we used is we have some alpha beta metric. Let's say we have an alpha beta metric, and the one form is parallel, then the connections are the same, alpha and Finsler metric.
Sorry to interrupt, but I don't think if you are using alpha beta metrics with a parallel one form, it will always be Ricci flat.
Exactly, and that will exactly be the problem. So,
yeah.
Yes, that's what I was getting at. So we cannot use our methods, and we need to do something completely different, which might be possible, but...
So I was really thinking of the case of Einstein metrics, which are non-trivial, so indeed not Ricci flat. Do you have some ideas on that?
Not specifically, no. So what we could try, of course, you have a solution which is not a vacuum solution, structured vacuum. Then you might have one form which is covariantly constant, but not null. So you have much more options for the one form. And then we would still have the same connection. And we might be able to figure something out here. But more than that, I don't know.
I have to say that I don't dare yet to go to the case of non-vacuum. I think that the vacuum case is...
Right, so by non-vacuum, I mean vacuum but with cosmological constant.
Yeah, okay. So what do you think about trying out Einstein spaces which are also weakly Landsberg? Do you think about this?
So you mean take an ansatz for one of these alpha beta metrics that's weakly Landsberg and then put in Einstein space?
Alpha beta matrix. Let's say something else, an alpha beta matrix.
Something else.
Yeah, so just thinking in general about whether you think that, if we take this equation, if we take let's say that the analog equation in general relativity, then we know that we will have solutions, vacuum solutions with an oscillator cosmological constant and they are Einstein spaces. So I'm just thinking of whether we could do something similar in this case. So but then with Finsler Einstein spaces instead of
right.
Not really per se alpha beta metrics and then if we could find Finsler Einstein spaces which are also weakly Landsberg, then what would happen to equation 7.7?
Yeah, that might be interesting. Yes, it's a good question too, because the nice thing in Riemannian geometry is that this equation, or the analog, is actually equivalent to being an Einstein space.
Yeah.
And the question is whether something similar holds in the Finsler setting. I have no idea, but that would be very interesting to look into. Yeah.
There is some work actually by a student of Professor Sanchez on the topic of Finsler-Einstein spaces, which are also weakly Landsberg. So I think that it would be very nice to use that. And, in this work, they proved that if you're in dimension 3 of larger than 3, and if you have such a Finsler-Einstein space, if it's weakly Landsberg, then yeah, the Ricci scalar will just be a constant multiplying f squared, the Finsler function. And I think that if you plug that into equation 7.7,
that sounds doable.
we may get quite interesting results. So,
yes, sounds good.
Okay, then since there is still about 30 seconds left, just a question related to the full field equation. So we were trying to find solutions, which were subclasses of Finsler spaces. So do you think that it would be really possible to find solutions to the full vacuum equation?
So you mean non-Berwald spaces?
I mean, yeah, fully general Finsler.
Fully general, yes. So I think in general that's extremely difficult, but one of the situations where it might be viable is if you look at small perturbations to pseudo-Riemannian spacetimes. So it would be very nice to look at gravitational waves and to try to derive the most general gravitational wave solution. Because here we did derive gravitational wave solution, but it's a very specific subclass, as you're saying.
Thank you very much. So, appreciated the defense, so please I'd like to ask the candidate and the seconds to return back to the seats in the audience. So the committee will retreat and we will move in space and time to the other room where we will discuss the quality and of the thesis and the defense, and we hope to get back very soon. Please rise.
Still alive. Nou, het zit erop.
Mega lang gaan zoeken naar. Ja, ja. Half kan niet. Moet ik even nog bij die tafel zien. Ja, dat heel kan toepassen. Hij wil gewoon niet. Ja, dat is goed. Maar ik moet wel zeggen dat ik wel denk dat
Ja. Kom maar jongens. Heb je een pen?
Heb je een pen? Ik heb toevallig.
Ja, zo, maar is
Oh jee, ik heb nog tijd. Ik weet al wat ik doe. Hoeveel ik weet het.
Oh, ik zie het een paar keer een sigma-gun, die is 2 keer negatief. Normaal is het maar 1 keer, dat min plus plus plus. Ja, en daar staat die plus plus min min.
Oh, ja, ja. Handtekening van een goede auteur. Ja, dat is goed. Ja, joh. Ik heb geoefend, hè?
Ja, tijdens de scheikundeles.
Ja, zeker.
Ja, dat weet ik nog.
Dat is ook zoeken lekker saai. Oh ja, zeker. Ja, oké, gaan we het over hebben.
Ja, top, daar hebben we zin in.
Zeker, dan de eerste editie.
Maar het is geen tijd voor wachten.
Het voelt wel goed. Ja? Lekker handtekening. I love you too, Random Citizen.
Dankjewel. Die heb je niet zien aankomen, wel zo. Nee? Heb je dit zien aankomen?
Zijn nou?
Heb je dit zien aankomen?
Nee. Ik ook niet. Wat zijn jullie voor rare mensen?
Nee, ik kan niet. Ga je dan weer met dingen voor? Ik bedoel, ik ga je niet zo vaak. Nee, weet je,
Zo, ja, dat was wel een ding.
Ja, man.
Ik ving hem al op. Ah, hij viel niet.
En dat was het niet gezegd.
Wel, gewoon. Ja? Ja, thanks. Dat denk ik toch wel.
Het heel veel jouw eerste verhaal, zo wat gewoon tijd.
Ja, dat was mijn hele doel.
Ook even doorgaan.
Ja, dat is het leuk.
Nice. Dat is echt nice.
Ja. Maar ja, we kunnen wel een abonnement binnenkomen, maar nou niet inderdaad. Ja?
Ja, heb je hem?
Jullie ook nog?
Ja, tuurlijk.
Terug naar de formaliteiten. Ja. Stelling. De deur is niet dicht. Hij zit nu op het vlak dat hij open gaat. Fotografisch binnen. Dus wat is het? Nee, dat is nog even.
Dat gaat automatisch. Die ene meneer die
Ja.
Please rise. Please be seated. I hereby reopen the meeting of this doctorate committee and kindly request the doctoral candidate and his seconds to take place here before the table. The doctorate board of the Eindhoven University of Technology, represented by us, has examined your dissertation and heard your defense of it. On the grounds of the aforementioned, the doctorate board has decided to award you the degree of doctor. I request that the first promoter acquit himself of the duties entrusted to him. Please rise.
Please rise.
Uit kracht van de bevoegdheid ons toegekend door de wet en namens het college van promoties bevorder ik u Sjors Heefer tot dokter en verleen ik u de rechten die verbonden zijn aan de dokterstitel. Deze toekenning geschiedt met het predicaat cum laude. Het diploma ondertekend door de rector Magnificus en de promotoren. En nu kan ik informeel van harte feliciteren met het geweldige resultaat. And I would like to give the word for the laudatio to Sjors' unicorn in the room. That's Andrea Fuster. He will speak to you with the laudatio.
Dankjewel.
Please sit down.
Oh, not yet. Picture time.
Ja, dat is goed. It's better to stand behind the mic if you want.
I think I can talk
Yeah, you can talk loud enough.
You can hear me?
Yes.
Okay, good. Zeer geleerde Dr. Heefer, beste Sjors. Laten we beginnen bij het begin. Er was een kans om een PhD aan te stellen vanuit facultaire middelen. Ik ben toen op zoek gegaan naar een geschikte kandidaat. En die heb ik gevonden in de Quantum Gravity onderzoeksgroep in Nijmegen, dankzij professor Renate Low. Zo ben je dus op 1 november 2018 begonnen aan je PhD in Eindhoven. Je had een traditie van Spaanse en Italiaanse vrouwelijke begeleiders bij je bachelor- en masterproject die wij op deze manier gelukkig konden voortzetten. Je bent maar meteen begonnen met de publicaties, met een artikel op Physical Review D over je masterproject, samen met je scriptiebegeleider Julia Kubitosi. In that year, 2019, we went together to the conference Geometric Foundations of Gravity in Tartu, your first conference, if I recall correctly. And let me also recall some ups and downs of that conference. Ups, you met quite some people in the field of alternative theories of gravity, in particular Nicoletta and Christian, whom would also become your most important collaborators. Downs, we almost didn't survive the conference outing, when we went for a walk in the forest and we literally had to run the whole way to escape from the thickest cloud of mosquitoes I have ever seen. After not too long, Nicoletta and Christian came to visit us in Eindhoven in the beginning of 2020. This was a very productive visit, which led to your first Finsler paper. The topic was metrizability of Berwald spacetimes, or actually non-metrizability. In your work, we came up with the first counterexamples to Szabo's theorem, disproving its validity in a Lorentz-Finsler setting. We also saw that physicists like us are actually able to prove and disprove theorems. Or maybe this only holds for mathematical physicists, I'm not sure. Kort na dit bezoek brak de coronatijden aan. Corona of geen corona, in coronajaar 2021 heb je 2 artikelen weten te publiceren. Eén daarvan was je eerste artikel over exacte oplossingen in Finsler gravity, namelijk de Randers PP-waves. Dit artikel kwam tot stand na een onschuldige vraag van Finsler-guru professor David Bouw tijdens een conferentie in Leipzig, nog voordat je begonnen was aan je promotie. Hij vroeg aan mij of er zwaartekrachtgolven oplossingen van het Randers-type konden bestaan. Waarop ik antwoordde, nee, natuurlijk niet. Maar zijn vraag was echter blijven hangen en jij bewees dat deze oplossingen degelijk wel konden bestaan. En dus David en Sjors 1, Andrea 0. En voor dit werk heb je ook nog een posterprijs gekregen tijdens een conferentie in Bad Honnef, mede georganiseerd door Christian. During your PhD, you have also been very active at the European Cost Action, Quantum Gravity Phenomenology in the multi-messenger era. And you went, for example, to all 4 annual conferences of the Action in Granada, Corfu, Naples, and Rijeka. And during the first 2 conferences, we continued with the tradition of conference disasters that started with the mosquito attack in Tartu. First, you almost couldn't come back from Granada due to the corona lockdown. And then we experienced quite a storm flood situation in Corfu. And luckily, no major disaster happened at the last 2 conferences, so the core seems to have been finally broken. And thanks to your involvement in the Action, you could contribute to a by now almost classic review paper in quantum gravity, phenomenology, and a white paper which is under submission at the moment. And although we, of course, don't care about impact factors, let's mention anyway that the review paper was published in the journal Progress in Particle and Nuclear Physics with an impact factor of 9.6. Not too bad for a PhD student in mathematics. We hebben samen een aantal bachelor- en masterstudenten begeleid. En 2 studenten wil ik hier expliciet noemen. Björn van Voorthuizen en Antonio Reggio. Met Björn hebben we gekeken of de kasnametriek gegeneraliseerd kon worden tot een oplossing in Finsler gravity. Dat was niet het geval, maar we hebben wel iets anders ontdekt. Björn had eigenlijk zijn verslag al ingediend, maar kwam opeens erachter dat er iets niet helemaal klopte. Binnen 24 uur hebben we 21 e-mails uitgewisseld met zijn drieën om dit proberen te begrijpen. Uiteindelijk is dit gelukt en zo kon Björn ook een bijdrage leveren aan een van je artikelen, alweer over metrizability. Met Antonio hebben we ook iets bijzonders ontdekt. De eerste non-Berwald Landsberg oplossing in Finsler gravity. Deze worden unicorns genoemd, omdat het onwaarschijnlijk is dat ze bestaan. Maar we hebben kunnen bewijzen dat unicorns wel bestaan. Tijdens het voorbereiden van deze laudatio heb ik geleerd dat unicorns ook iets anders zijn. Namelijk start-ups die een waardering hebben van meer dan 1 miljard. En nou, dat hebben we jammer genoeg niet gedaan tijdens de promotie. En nu even over minder leuke dingen. Vorig jaar werd ik zelf onverwacht ziek. En daardoor konden we helaas weinig interactie hebben tijdens het laatste jaar van je PhD. En toch was 2023 heel productief. Je hebt niet alleen je proefschrift geschreven, maar ook 3 artikels gepubliceerd. And an important milestone of your PhD also happened last year, your first paper without Christian as co-author. En zo zijn we aangekomen bij 2024, het jaar waarin je promoveert. En je doet dat niet zomaar, want je promoveert vandaag cum laude. Iets wat ongeveer 1 op de 20 promovenden lukt. Daarom wil ik jou, je familie en vrienden van harte feliciteren met deze bijzondere prestatie. Wat de toekomst hierna nog brengt, weten we niet, maar gelukkig blijven voorlopig onder ons als docent. Iets wat jou ligt en waar je heel goed doet. En binnen je huidige aanstelling heb je ook een beetje ruimte voor onderzoek. En ik kijk uit naar een verdere samenwerking op het gebied van Finsler G², ofwel geometry en gravity. Daar moeten we waarschijnlijk eerst aan de slag om een ander kwadraat af te ronden, dat van quadratic gravity. Sjors, nogmaals gefeliciteerd en geniet van deze dag.
Dankjewel.
So, esteemed young Dr. Sjors Heefer, on behalf of the doctorate board of the university, I congratulate you with the degree. The degree of doctor has rights and obligations, and I need to read them out. As a holder of this degree, you are committed to standards of scientific integrity, trustworthiness, intellectual honesty, openness, independence, and societal responsibility. These standards are described in more detail in the Netherlands Code of Conduct for Research Integrity and in the Eindhoven Code based on it. You also have duties towards society. You must be clear about the boundaries of your own expertise, and you must communicate honestly and independently about the results of your work, including potential risks associated with it. You are committed to the ethical codes for research and design involving human subjects or animals. Serious words, I think also necessary in the society of these days. But for now, I hope this is going to be a much more joyful day. So it's a real pleasure again to congratulate you with the success, and of course also friends and family. I hope that you will have an enjoyable day. So I would like to ask you to go back to the seats, all of you, to the seats in the audience, so that I can finalize this session. So I'm about to close this meeting, but I need to explain a few things before I do so. So immediately after I close the meeting, we are going to take a photograph. It's in the back, she's in the back. And we are going to do that outside this room. That also means we are going to congratulate the new doctorate later, after the photograph, so after we've left outside. So when photos have been taken, first with the committee and the new doctor, and also later with others if you wish, we can congratulate, and then you will be in charge of the rest of the day. So I would like to now formally close the meeting and move to the more, nice parts of this defense.
Please rise.
Mag ik jullie verzoeken? Gefeliciteerd. Ja. Gefeliciteerd. Gefeliciteerd. Eerst
Bij twee.
Ze allemaal de jassen meenemen. Nog niet, je hebt ze wel even.
Sorry to resist.
Dit is part 1, dit is deel 1. Deel 2 staat hier, denk ik. Ja, ik onder de familie. Daar gaat het.
I need to go to the right. Please come here.
Officieel.
Mooi.
Dankjewel. Dankjewel. So, thank you guys.
Congratulations. Really, really awesome.
De moeder nu? Echt zo leuk.
You answered it was really good. Very good.
Good to hear.
All the stuff off.
what he has promised you, but then he, I think, is in charge of drinks and something like that. I will not join you
Jij werkt samen met Sjors. Ik snap er allemaal niks van.